All right, so why did we bother reviewing radicals? It's because this is the way we're going to synthesize organohalides, right? We're going to synthesize organohalides through radical halogenation. So we already did a little bit of this, so review. Again, your radical reactions, remember we can take methyl, add some chlorine gas to it, add some UV light, and then we can replace the chlorine. And this actually can continue on to form something like dichloromethane, continue on to form chloroform, and then continue on to form carbon tetrachloride. But we can do this with other compounds as well. So let's take a look at what the energetics of this is. So we have a methyl X2, adding some UV light to this. To form our products, right? And so we're going to take a look at different halogens, and then we're going to look at the enthalpy of this reaction, which is going to be approximately equal to the delta G of this reaction because the entropy of this doesn't really change much. These values are in kilojoules per mole. And so our options are fluorine, chlorine, bromine, and iodine. And the values here are negative 431 kilojoules per mole, which is hugely exothermic, negative 104 kilojoules per mole, which is also very exothermic, negative 33 kilojoules per mole, exothermic still, and then plus 55 kilojoules per mole. So let's take a look at some of these values. First off, this 431, this is just massive. And so it's too exothermic to be practical. If you start this reaction off, you're just going to produce so much heat, you're essentially just going to instantly make an explosion. And so we're not going to do these reactions with fluorine because it's dangerous. And then iodine, we can see that one's positive, and so this one's not even going to happen. And so we're mainly going to stick with chlorine and bromine. And so let's take a look at what happens when we take propane, add some chlorine gas to it, and add some add some light, right? Some UV light. We'll get our chlorine in the secondary position, and this makes sense because the intermediate here is the secondary carbon radical, which is more stable, but we'll also get some of the primary as well. And if we take a look at the ratios, this is approximately 60%, while this one is 40%. And so we can see that our rules do hold true. The secondary is favored, but it's not by much. So what we say is that chlorine is not very selective. And so that's not very useful for us because if you think about every time you do this reaction, now the first step, you got to do the reaction. And then the second step, you've got to separate these compounds that are going to be very chemically similar to one another from one another. And so that's just a huge pain in the butt, and we want to avoid that if we can. If we take a look at the same reaction now with bromine, remember this is much less exothermic, and so it'll go a little bit more slowly. And this will get much better results. So if we take a look at these, we'll see that we get 97% of this secondary, and then only about 3% of this primary. And so the end story here is that bromine halogenation is much more selective. And so if you want to halogenate anything other than methyl, you're going to want to use bromine. There's better ways to make the organochlorides, iodides, and fluorides, which we'll learn about later. Let's take a look at this just as a little bit of a refresher. And so for this one, I want you to identify what is the major product. So this is going to be something we're going to be doing a lot in chemistry, is identifying the major product. I don't want you to tell me every product. I just want you to tell me what the major one is. And so if we think about this going on, right, remember the first thing we're going to do is form a bromine radical. This one's going to react with the most stable radical. And so if you think about where we're going to form our most stable radical, it's going to be this tertiary radical. And so they'll combine, and our major product will be our bromine right over here. Let's do another example. In this case, now we have a stereoisomer, right? And we have identified that we just have one of our stereoisomers, right? And so let's see what's going to happen when we do this halogenation with bromine. And so again, the first thing that's going to happen is we're going to form this bromine radical, and it's going to abstract one of these hydrogens. It's going to be the most substituted hydrogen, which is this tertiary hydrogen right here. And so in this first step, right, it'll form HBr. And then we can think about the radical right here. But now we have a radical here, which means we've destroyed the stereochemistry of this compound right here. And then this is going to react with a Br2. To give us our final product. Of this guy right here. And this is going to be racemic. Right, so even though you started off with one hand of the molecule, because of the mechanism, you destroyed its stereochemistry, and so you get a racemic product, right? It's still a stereocenter, but it's not specifically an R or an S. It's a mixture of the two. So just another thing to keep in mind when you're doing these halogenations.